follows actually. That is, um, I forgot that book's name. Ancillin. Let me share my.
Sir,
One second, one second. Let me present. I will share all the books which you are looking for. I will share. Wait.
thank you, sir. Very kind of you, sir. Very, very kind of you.
So now my screen is visible to you, right?
Yes, sir. Visible, sir. Visible.
Actually, I am having problem with recording. That's why making some disturb. Anyway, it is getting recorded. My face is not visible. Anyway, I will go with it. So let's go ahead. Ancillin organic chemistry. This one. Actually, ma'am follows this book. So if I directly go to Amazon, you will find Modern Physical Organic Chemistry by Eric B. Anselin and Dorothy. Dorothy. So this is a very popular book. This is a book on physical organic chemistry. Remember, this is not just organic part. So that the physical part is there. Physical organic chemistry. This one, and then you got it the book right, and Claydon Organic Chemistry. If you search for it, so you will find a lot of this. See, this at the right you see there Organic Chemistry by Jonathan Claydon, Nick Greaves, and Stuart Warren. So I see three authors are there currently which is available. But earlier there was another person who was there, but his name is not anymore. So this book, this is a, I mean epitome. I mean, this is the best book I would say to understand things. So this book, and then there are this is a very standard book for introduction of organic chemistry. This is a very mechanism. This is a very good book. Okay, so a guidebook to mechanism in organic chemistry by this
Sure, sir.
one.
Sure, sure. Thank you, sir. Thank you.
And this three book is enough. I mean, you don't need much than that. Oh my God, there is no only three people. Okay, no problem. Okay, let's just start. Okay, I want already seven.
Sure, sir. Sure, sir.
Mm. So welcome to NPTEL Day 7 Reaction Mechanism in Organic Chemistry. So today we will talk about basically from week 7. If you follow the course, where different intermediates or short living entities are trapped, and that's how we can say okay this reaction follows this species. Otherwise we cannot say that this mechanism is correct or the other mechanism is uh, not working. So basically you cannot establish a mechanism by saying that okay this is the mechanism. You can only do this by saying okay those mechanisms are not working, those are not possible, hence this is the mechanism. This is the only possible way to say. Again I am repeating, you cannot say this is the correct mechanism. You can only say that other mechanisms are wrong, that is not possible, so this is the mechanism most probable. So this is the important point. Let's go ahead. So basically I will show some reaction. These reactions are very popular. In any book you will find these reactions and their mechanism. By the way, I will show the mechanism. These are very easy to follow, and in between there will be some intermediates. Our goal is to understand the intermediate. I mean, how can we track okay this is the intermediate, what, how do you say this without any extra words. Yes. So one of the first intermediate which we observed in aromatic system is benzene, which is like benzene, and imagine one carbon carbon bond is double bond is like triple bond. So that's a benzene in, I mean it looks like. Then how do you trap this? You can trap this using cycloaddition reaction. So let's start with the reaction, which will show what is the benzene, how can we make it. So it's a simple reaction where you have amino carboxylic acid aromatic system. So amine NH2 group, and then carboxylic acid is also there. So if you treat it with RONO, basically some acid RONO, then what will happen? This NH2 group will be functionalized into diazo group. So N2 group is formed. Now this C double O minus removal of carbon dioxide will give you this kind of species, which is intermediate we call benzene. Well, we have a friend. Let's see. Let me further check I am recording or not. Yeah, I am recording. So what we have is a intermediate benzene. I think this ma'am has already all these things are shown. Okay. So our goal is to capture this benzene. How do we do this? Uh, Initially we didn't say any reaction, or it's okay. So let's go ahead. So we have a benzene. Now there is one part of the trapping, which is I am saying it cycloaddition reaction. So here is the mechanism to follow. So we showed that there is a formation of benzene, right? Now if you treat it with anthracene, so this anthracene, it will undergo cycloaddition reaction. Basically 4 plus 2 cycloaddition. What is that? So you know that in anthracene, this in the middle benzene, it has a less aromatic character kind of thing. So basically, what I mean is that this two pi bond, which is shown here, these are, if not full, but somewhat partially behaves as if a double bond kind of system. Okay, so this pi bond, and then this, if you can consider it as if it is an ethylene. So not ethylene exactly, but we can consider for the sake of simplicity here. So this will undergo cycloaddition reaction to form such an species. At the right side you can see it's look like a propeller tree. In the submarine you can see such kind of structure, I mean similar structure. So the mechanism is further shown in the books in the Clayton, as we are saying. Okay, we have another friends. Please try to join at least 7-5. Don't make. So we have such mechanism. If we show it in terms of arrow pushing, please join at least by 7 or 5. So our goal is to capture the intermediate, which is benzene. We can do it by treating with anthracene and forms an adduct, which is shown on the right side. Now the mechanism in terms of arrow pushing, we can show it like this. Benzene's pi electron is coming here. This pi electron moves here, and then this pi electron goes back. Overall, this forms green colored, shows you that these two bonds are formed, and this MO. One second. Please everyone join at time. So there is some other descriptions is also shown, like in terms of MO, which I am not going to discuss anyway. So these forms are adduct. Now actually I should have shown what is the reaction first, but anyway it's okay. Now I will show some reaction and it will be more clear to you. Before I go there, there is a similar situation is also here. So here we have a dihalosubstituted benzene ring, which on treatment with lithium amalgam, so lithium Hg, we expect a product A. This A actually an intermediate, which is benzene. This mechanism is not so clear. Not so clear in the sense that I didn't find any explanation how it is going, like which bond is forming or breaking. Overall, it's like you do the experiment and you got some intermediate or kind of thing. So you got a intermediate A, which you treat with furan. Let's say in your system furan is there. So what will be the case here? So this I will show by drawing. one second. So there I go, whiteboard. So the intermediate A is what we have a benzene ring. So this is an intermediate, okay, and it is treated with furan. So this system, in the earlier example we showed anthracene, right? We showed anthracene. So there anthracene acted as a trapping agent, okay. So here in place of anthracene we have what do we have? Furan ring. So again we can think of it as a 4+2 cycloaddition reaction. How do you show it? It is very simple. Let me show it in a different way. So this is the situation. Now I will just show the arrow pushing mechanism, which is pretty easy. So this electron will come here. So we go here. Sorry. So overall, let me erase something. This part. I hope the arrow pushing is clear. It's very easy to follow. Okay. So what will happen is that we got a product. It will look like. Okay. So it will look like this. Okay. So this oxygen ring, it's now see, the bridging position is there. So oxygen is at this position. This carbon CO bond. So this is the CO bond. This is the CO bond. This pi bond has formed here. This here. So this is shown here, and the benzene. So that's how, I mean, this furan or thiophene, which acts like a dying kind of system. So whenever see any system which is kind of this dying can act as a trapping agent for benzene. Okay. Now, whenever you come across some reaction, when you think, okay, it is undergoing through benzene, to prove the hypothesis, okay, it is really going through the benzene, you have to do some such kind of experiment where you extract the benzene and show that such adducts are formed. So overall, this is the funda here. Now let's go to some other reaction. So B is the product I have shown. Now, so it is not only the thing that trapping intermediate is required to prove or disprove any mechanism. You can also do leveling experiment. In the leveling experiment, what we do is the particular atom which is of our interest. Let's say here the ipsocarbon, the carbon chlorine bond, carbon attached to the chlorine is of our interest. So what we will do, we will substitute that carbon atom with its isotope. So basically we are trying to distinguish between the carbon atoms. So let's say initially it is 12C, so we will replace it with isotope 13C or 14C, whatever. Now one may say that let's say we don't know any mechanism. So and the product obtained is, sorry. So let's say we don't know anything about the mechanism, what it follows or anything. So basically we have a benzene ring, the chloro substituent, and we treat it with KNH2. and we got amine in place of chlorine. So what will be the initial hypothesis in terms of mechanism? Let's say someone doesn't know anything about benzene or anything. So at least I will assume that okay, it's a just like a substitution reaction, normal SN2 kind of thing. One can think. I mean, at least this is a, if it is very bad or good, I don't care actually. It is possible or not, we are thinking K plus NH2 minus. So seeing from the product side, we can think like, okay, this is going like this and this is like this. So this is a mechanism number one we can think of. Okay, right? But this mechanism should be proved. And sometimes someone says, okay, this is not the mechanism, it is going through something else. So someone proposes like, okay, it will abstract this hydrogen, it will forms then intermediate kind of this benzene intermediate, it will form, and then NH2 minus will attack, NH2 minus will attack here, and then it forms the aniline here. So this is another mechanism. So mechanism 2. So from then if I say this is forming and this is the mechanism which is actually followed, then we have to prove that this is formed. So one thing we can do, which is already shown, that we can trap this intermediate. That's how we can say that this reaction follows this path, not the elimination substitution path. Anyway, we know that this in aromatic uh, hello substituted benzene, this substitution doesn't occur actually. Okay, so another way of proving this is labeling, which we are talking. So let's make clear the frame, and what I will show here is very easy. uh, so I have chlorobenzene, and this is isotopically labeled, this carbon atom. Okay, now what will happen? So Cl is there, and let's say hydrogen is there, and we will get an intermediate enzyme. If you are interested, go look at the structure of benzene. Okay, this pi electron is not conjugated with the other. Hmm? Basically, it's in a p orbital. So what we have is this. Now there is NH2 minus. So what do you expect? NH2 minus to attack at which position? So basically, these two positions are same. So we these are just isotopically different, these two carbon atom, but the chemistry is same. The physics will be different, but the chemistry is same. So these are same, right? So these two are same, and that's why there is 50-50 chance of attacking here and attacking here also. So if I label it as 1 and label it as a 2, anyway, I have already labeled with star isotopes, so that doesn't make any sense. So let's say 2 attack here, and then this arrow pushing is very any bad. Sorry. So what we expect? We expect to have product. Let's say I am showing here 2. Okay. So it will be like NH2 will be here, and in the other cases, let's say 1 here I put. So NH2 is here. Now the difference is that here the isotope was here, and here the isotope is here. You got the point? So these will show the difference actually. If it is a normal if it is a normal like substitution, what you would end up with? Only one thing. You will get only this product. If it is a, this is the situation, but this is not experimentally observed. So this is 100, not 100. I mean, this is not observed. If it is what the case, so it is not the case. Rather, what we see a mixture of these two, around 50. I am not saying exactly 50. Let's say 47 or 100 minus 47 is this part. So this isotopical substitution shows that this is formed actually. So there is some intermediate is formed which is same. I mean indistinguishable in terms of chemistry. So this 1 2 are equivalent. This is the correct term. So this 1 2 are equivalent. So and there is no difference between the, at least in chemical. So there is no difference. That's why NH2 can attack at this position or at the isotopically substituted carbon atom, giving 50-50% of these two products. So that's why these leveling experiments are very important along with trapping intermediate. Now let's go ahead. What else do we have? Now whatever I've shown is already talked in the book. So it looks like this. So here it is shown like a 14C and it abstracts this hydrogen, forms benzene. Now there are two chances whether it can attack isotopically substituted carbon atom or the normal carbon atom, thereby giving two products at the right side, you can see. So this is the observation. Now if I ask you what will be the situation here, uh, first can you guess what is the product here? So I will give you just 1 minute. What will be the product for the last reaction? It's the very same reaction, just asking what is the product here. Can you see
Sir,
this?
intermediate is intermediate is benzene only, no sir?
Yes
Intermediate
sir,
is
exactly,
benzene.
exactly. It is same.
And phenyl, biphenyl is a product. Biphenyl.
Biphenyl. Exactly. So pH minus will attack, and again we will see the same observation of this around 50-50 formation of product. Okay. So that I'm not going to show. Let's go ahead. What else do we have? Okay. So another interesting thing is the crossover experiment, which I will show. Anyway, so it say the Claisen rearrangement. The question poses is intermolecular or intramolecular, and we say that the solution is crossover experiment. The goal is to here we want to know a reaction is following intermolecular or intramolecular pathway. Mm, so before I discuss the crossover experiment, I will discuss what is this Claisen rearrangement with a simple example. Okay, so let's go ahead. Again, we'll go here, clear the frame. So imagine you have a benzene and basically an ether I need. So CH2 and then double bond. Again, it's a class of pericyclic reaction, just like I have shown in the very first slide, trapping the 4+2 cycloaddition reaction. Here, what happened? It's a concerted mechanism, and that's I shouldn't say this actually. What kind of mechanism? So anyway, imagine someone proposes this idea of mechanism. Someone say, okay, it will go like this. It will like. Let me change the color. Sorry. Imagine you don't know the mechanism. So we'll initially proposing this mechanism. Arrow pushing is our best friend. So what do you expect? So this bond is there, no problem. This has become double bond, so I will put oxygen here. This bond has broken. This has a formation of double bond. This has become a single bond. There is been a form of single bond. So this is the situation, and of course remember there is a hydrogen here. In the next step, it will go like this, and it will go like this. So very simple. So again we are back with our benzene ring, OH. So this is the situation. Okay. Now let's say someone proposes this mechanism, but whereas someone else may propose another mechanism. Let me show it in a different color, green color. Let's say someone says first there is a formation of O negative charge, and this bond is breaked. Like if I name it, label it as a 1 2. Okay. So this is bond is break. Sorry, see. So this is a forms an allyl carbocation. So you see this is an allyl carbocation is formed. and of course you can show the corresponding resonating structure like plus is here. Overall it is like allyl carbocation, so I will show plus here. Now what can happen, this O negative charge can put here and this can attack allyl carbocation, and we come up with the same similar intermediate which was shown in the earlier cases in the red color. There is a hydrogen and it will go like this and it will go like that, this and that. Anyway, we get the product. Okay, now the question is, how do you know that it is the red pathway it is following, not the green color pathway? So that is the goal actually. This is the problem statement. So in such a case, a crossover experiment will tell you the situation actually, whether it really dissociates or it doesn't really dissociate. It follows a concerted path here like this. So what happened? That is the question. Now let me show the question again. So here you understand the Claisen rearrangement, right? Now come to this two reactant. Now if we don't know, so what will happen? If it is intermolecular or intramolecular, we will have different products. So let's see. Again, I will go same thing. I hope it is very clear to you. It will be clear frame. And I need the structure of those. Yeah. Come on. Just a second. Sorry. So what we have is okay. Mm, uh, okay, I'm not drawing through all the part. Okay, just I am showing the product. What will happen? You can figure it out easy, right? Clear frame. So if it is there is a fragmentation, we will have this cation, right? Allyl cation. So there will be this charge from the first reactant, and from the second part we will have this, and then this. There is a pH. So these two will be formed if it is following the green pathway which I shown earlier. Okay, so these two will form. Now in the other side we have it is not shown. So we have O minus here from the second reactant, and from the first reactant what we have, uh, naphthol naphthoxide. Okay, so these two are there. If it is follows this mechanism, so then what can happen, it can combine with this carbocation, it can combine with this carbocation, so it will give two products. Similarly, this can combine with this carbocation, this can combine with this carbocation. So overall we would expect four product if it is really follows this mechanism. Okay, so if it is intermolecular reaction like this, so we would expect four products. But interestingly, in the experiment, when you do, you don't get four products. You get only two products. And the two products are basically, let me, again I have to clear this, control Z, get the frame. So what you actually experimentally observed are, you have OH here and this CH2 and then double bond. This is one product is found, and in this case there is OH And now there is some interesting thing here, so it will be better to show you actually. So what will happen, I have double bond here and then the pH. So the product will have this will come here, right? Just follow with me, it will be clear. So I will make a bond here. Let's do it. So it will be benzene ring. This position will have pH actually, and this bond has broken. Just a second, okay. Something is missing. This is okay. What is wrong? Can you guess it? Huh. Okay. I did. That's what this I have drawn in a wrong way. Let me do it in a new frame. That reactant I have drawn improperly. So I have O. There is I need a CH2 and then double bond, then pH. Now it will be clear. Now it makes sense actually. So this will come here. This will come here. This will go there. Just make it benzene, okay? Don't worry. It's a benzene thing. So this will be there. I'm drawing just the product. So this will be the product, okay? Overall, our conclusion is that we get only two products experimentally, and there is within this crossover experiment. So basically, crossover experiment means there are similar two reactants are there. There is no separate entities are formed. It's a concerted mechanism, so there is no crisscross. It going to the other reactant, one part going to the other reactant. It is not like that. So this is one thing. And now, if I ask you another experiment which can say this, it is and such a thing, and isotope labeling can also do the same thing. This is shown here. So in this experiment, you will see that isotopically this carbon will attach to this ortho position of the benzene ring. So it will come here. I'm not showing the mechanism. I will just show the product. Okay, it's already I have shown. So okay, sorry, clear the frame. So basically, what you will get, the isotopically carbon will be here. Just note the position; those are important. So this will be the case here. And let's go with some other reaction. This was cool. Now this is another rearrangement, and there are a lot of studies on this, and name is Beckmann rearrangement. So I hope you are you know this reaction. If you don't know, I will just show it in a very simple way. So you have this oxime, R1 R2 to substitute NOH. If you give catalytic amount of acid, you get the amide. So R2CONH R1. So this reaction, some basic informations are like this. The group trans to the OH or anti to the OH living group, any living group like OH which will be leaving. Group migrates. So R1 has migrated to N. That's why you can see that NH is with R1 and R2 with the carbon, R2 with the carbon. Now let me show the mechanism, and then I have some questions on this. Sharing. Okay. So what we have is very simple. R1 and then A. Sorry. Oxygen. So this sorry. So there will be OH, and this is a nitrogen atom, and this is a carbon atom. This is R2. Perfect. So if you treat it with acid, this will be protonated OH2 plus. Sorry. And now the question, which group will migrate? As I said, the trans to the leaving group will migrate. So this R1 group with its bonding electron pair will migrate to the nitrogen atom, and this will leave. So what we will end up with, so remember there was R2, and this will create a positive charge here, carbocation, and nitrogen with a R1 group. This is the situation. Now there will be water in the system. We are assuming acid catalysis. So it will attack here, and I'm directly showing it as if proton is removed. So OH. Remember there are multiple steps. I just showed in a single step. R1 and there is R2, and this will undergo some tautomerization. This, and it will go like this, and what you end up with, the corresponding amide. So this is a very simple mechanism. Now here comes the question. So I hope you understand the mechanism. Please see, it's a simplified version. Okay. So the main point which is important to our discussion is this, that R1 group is migrating here. What will happen actually, this is I am showing in a single step. R1 with its bonding electron pair going directly to this. Now imagine it can leave as R1 plus carbocation, and or R1, sorry, R1 minus. Okay, it can leave as R1 minus, then it can do the thing. Okay, that is also a possibility. Now so such things will be discussed in this next question. So for example, you see this reaction. In this reaction, the anti group or trans to the OH leaving group is this part, which has the chiral center attached. Chiral center is there. Now you see it has undergone migration from this center to this nitrogen. That's why it is this NH group is attached to the chiral center, and the CO PH, right? Now this Beckmann rearrangement, it shows that this part, this chiral center, has retention of configuration. Again, let me say it, retention of configuration, meaning that the it has directly undergoes and migrated to the nitrogen center. So if it was not concerted path, what will happen? So it will form a planar species. In that case, this will not be observed. So in that case, R will be formed, both will be formed, R and S. So this part shows that there is a direct jump from direct migration from this center to this center. Now this is pretty simple, but if we go to the next example, it will be little interesting. So what do you expect the product of this crossover reaction? Again, our interest is in the crossover reaction. That's why I wanted to show the Beckmann rearrangement. Other than that, that is not of our point interest. Now you see this reaction. It's a very simple reaction. Again, Beckmann reaction. What do we expect? This tertiary butyl group will migrate, trans to the OH group, and it will form this. So if someone asks you what is the mechanism of this reaction, you can directly show that it's a concerted process, that tertiary butyl will with its bonding electron pair will migrate to the nitrogen atom. But what experimentally is found, it is not that situation. Something else is happening here. Again, I am saying it is not the simple situation here. How do we show this? We do a crossover experiment. How do we do a crossover experiment? We take different group at this position and this position. So I have a question like this. Now see, as with the Claisen rearrangement, there will be two reactants. See, and we put H plus here. Now imagine we don't know the reaction mechanism. So what we will expect based on our previous study? So this will come here and you will get a single product. This will come here and you will get a single product. Meaning that, let me show it. This may be a little difficult, but it's not that much. Please just Control A. Sorry, clear the frame. Now for the first red color substrate, we expect to form like something like this: COMe and then NH tertiary butyl. This, and the black color one we expect to be have CO PH NH CME2 PH. Okay, CME2, and there is a PH. These two product we will expect. Okay, this will be the case, this will be the case. So crossover experiment should have these two product. If it is like concerted way, like a direct migration of the tertiary butyl or any other group, and then simultaneous leaving of OH2 plus. But in this case, it is interesting to observe that the mixture of product was obtained. That it was not only these two product plus something C plus D was obtained. Now the question is this: then what is the mechanism? The question is, we don't get only two products, we get four products actually. So what is the situation there? The situation is explained in the next slide, is like this. Oops, I have not included those. Anyway, it's very easy. It will take time to draw, so I will show it in the directly. So basically what will happen, since this part which group is migrating CMe3, see, so if it is forms a carbocation, that's a very good stable carbocation actually. So it's a very good stable carbocation, and here also PHCMe2 group is also a very good stable carbocation. So this is the force which gives the direct migration is not allowed. So I will go to directly book, which will be easy to follow. So just a second. So you follow with this, you will get 987. Sorry. So you see this situation. Please concentrate here. So the situation is like this. So this bond can give you this carbocation, right? So this will give you one carbocation, and the second reactant will give you this carbocation, and therefore each cyanide which has formed, it can go either with this, either with that, and this can also further react with the two entities. Thus you give it four different amide. So this is the situation in this crossover experiment. So from the crossover experiment, you can distinguish between this intramolecular or intermolecular rearrangement. Basically, these are rearrangement. So in the Beckmann reaction, actually, depending upon which group is migrating, again I am saying, in the Beckmann reaction, depending upon which group is migrating, whether this can form a tertiary, important stable carbocation, then it will follow such mechanism. In other cases, it will directly, in a concerted way, it will move, and leaving group will remove from the system, which was shown in the chiral carbon containing center. So this is the situation. There will be four mixture of products. I will take some 5 minutes to, if you have any question. Any question? Are you getting this? Okay, some of people left. Any question? Okay, no problem. And then we have few more questions we will discuss, and we'll stop. Now, what else do we have? reaction may not go as we expect. For example, if you let me discuss this question. So here what happened? We will expect a simple HCl addition reaction, right? The alkene will attack H plus, so there will be carbocation formation, and then the Cl minus can attack in a, depending upon where H plus get added, Cl minus can attack in a two different way, and this is the product. But interestingly, none of them are observed. So the question is, can you guess then what is the product or what is the intermediate? Now I will give you some time. If you are interested, you can solve it. What will be the situation here? Venkatesh, I hope you are there. Check. Anyone? Any response? Did you write the question? Okay, seems no one is there. No problem. Then,
Sir, maybe H
uh,
plus H plus may attack at ketonic oxygen, carbonyl oxygen.
okay, then,
Then it form carbonyl at
hmm,
the carbonyl carbon.
then,
Then kind of rearrangement. Double bond is there, so
uh,
rearrangement.
yeah, that may happen, but this pi electron will have more propensity to attack on H plus in presence of carbonyl also. So what will happen?
Okay, sir.
Let me, only a few are there. uh, Paranathaman and Ankita and you, Venkatesh. So it's okay. So I will show it. It's a nice example actually, which illustrated different concepts. So you see here this this presence of a nucleophile, this oxygen with its lone pair, when it's abstract H plus, and then oxygen will directly attack here. You see, and it forms this 5 5 bridge system, ring system, and then Cl minus attacks here and it forms this system. Okay, so this is a little tricky. So if someone asks you what will be the intermediate, so this is the situation actually. This is quite stable, and you can think of another possibility, like if H plus is added at this carbon, if H plus is added this carbon, you will have a 6 by 4, which is not so stable, 4 member ring. Here the carbocation stability is both more or less same, whether hydrogen add here or add here, same, but the ring system will be different, 6 4 and then 5 5. So this is much more stable. And I find another question which is not discussed in the book also.
Sir, can you please repeat, sir? Can you please repeat?
Okay,
Can you
okay.
please repeat, sir?
Let me show, let me show. Mm, it will be here. So I have a 8 member ring. So this is K2, this is oxygen. So this is the system, right? So imagine there is a this pi bond will attack H plus, huh? So the question is which carbon will attach to this H plus. So there are two possibility, right? So I will show it here. The one possibility which is shown already, I will show. It's a hydrogen attaching here. So there is a plus charge here, and you have oxygen at this position, carbonyl group at this position. Now oxygen with its lone pair will attack. Sorry. So what is the situation? 1, 2, 3, 4, 5, 6. So there will be one 6-member ring, and this oxygen and this 3 carbon atom will form a 4-member ring. Did you get it? So let's say oxygen is here, 1 carbon, 2 carbon, and So let me directly show it in this bond here. Before I do that, clear, erase this. If I erase this arrow pushing mechanism, it will directly show what is happening. So you see this 4-member ring and you see the 6-member ring. Did you get it? OCH2, there will be carbonyl group here actually. So this will be formed. Whereas if you attack the H at this position, green color, if you attach the H plus here, and then the positive charge will be here and oxygen will form here. So this will be 5 and 5. Now it is clear, Venkatesh?
Yes, sir. Yes, sir. Thank you, sir. Thank you, sir.
Okay.
Clear, sir. It is clear.
Okay, now see, I also have one doubt here within this question, which I didn't find answer in the book actually. Maybe some reason with this carbonyl group. Why the Cl minus attacking at this position, not the other position? Like it could have attacked here also, right? Cl minus is attacking here and then giving you this product. This is experimentally observed. Anyway, we are not going to that. Now I have some other thing. Uh, I don't have much time. There are a lot of things here. So you have this alkyne. Now you treat it with bromine and acetic acid. So you will get bromine addition, right? One bromine will attach here, one bromine will attach here. So this is shown here. Now the question is, what is the geometry of the double bond in the product? So it is either cis or trans. So this question is a little bit actually cis or trans. Now if you have given x equal to OMe or CH3, I have 4 options. Let's say this is your exam. How will you answer it? Look at the question carefully. And let me check who is there. Christina, I think you left and then joined. Ankita, Paranathaman, and Venkatesh. Anyone interested to answer the question? It's not that, I mean, you can think it of, it's not that difficult or neither that easy also.
Sir, in the case of CF3, highly electron withdrawing group,
Hmm.
trans, and in
Trans.
the case of OME,
Hmm.
OME cis.
So
Option 3,
OM
sir.
is CF3 trans. Question option number 3.
Yes, sir.
I think you are right. Let's see. I have already shown the mechanism here. It's actually, this example is very interesting. I liked it, and anyone will like it. This is a very good example. So, what is the mechanism then? What it is following? So, so this is the situation. Ma is cis, and with CF3 it is trans, which is correct. Nice. And if you see the mechanism, it is another interesting aspect. So when there is CF3 group, it's a simple bromine addition in the very first step. We expect in this bromonium cation, and of course the bromine will attack anti-addition, so we get the antiproduct, no problem. But when there is OMe group, the electron richness of the benzene ring, see what happens here. The OMe pushes its electron and through the benzene ring and forms a cyclic, this intermediate, spiro kind of intermediate. See, now here the bromine attacks at this position and opens the 3-member ring to give you the cis products. So it's very interesting that a substituent can change the altogether mechanism itself. So this is a very minute details, like a substituent which is electron withdrawing group can give you anti or trans, or when substitution when there is electron releasing group, by virtue of its high electron density, the pi electron, benzene pi electron can form a intermediate like this, and therefore the cis product is formed. This is an interesting aspect, and I will quickly show this example and I will finish it. Okay, so this reaction is also again interesting. So you see there is a red colored cis double bond, and in presence of H plus, it isomerizes to the more stable trans double bond. Now the question is, what is the mechanism? How do you know that this is the correct mechanism? So you see, imagine I propose this mechanism. What will be happen in the first step? Alkene will attack an H plus, then there will be carbocation formation. It will rotate. This single bond can rotate anyway, and then the hydrogen will eliminate, and you will get the E. So it seems so good. The mechanism is so perfect here. There is no loophole in this. One may claim that okay, this is the correct mechanism, but actually this is not the correct mechanism. Something else is going on. So if you do the reaction in deuterated solvent, like I mean D plus and D2O, rather than doing it in H plus and H2O, you do it with D plus and D2O. So what will happen? It is like this. So rather than this pi electron attacking to H plus, it happens that this pi electron attack the D plus. So if I label it 1 here, 2 here, 3 here, 4 here. So 4 number carbon attack the D plus. So this will enriched, this carbon, last terminal carbon will be enriched with deuterium. And see, the carbocation is much more stable here also, because it is benzylic as well as allylic here. See, double bond is conjugated with the carbocation and the benzene ring is also conjugated. You compare with the earlier situation, here you see that it is only benzylic, not allylic. Here it is both benzylic and allylic, which can then undergo rotation. Now it can go undergo elimination. Elimination to give you the product. So this is the mechanism. So it gets elimination and gives the product. So this is the correct mechanism, not the earlier one. Now you may ask a question, why these hydrogens are, it may happen that deuterium also be eliminated. But see, there are 2 points which are discussed. One, there are 2 hydrogen, 1 deuterium. So possibility in terms of probability, hydrogen will be eliminated. Again, there are second aspect is that carbon deuterium isotope effect, you know that CD bond is much stronger, little stronger compared to carbon hydrogen bond. So the chances are CH bond will eliminate. The main point is that you get a enriched terminal carbon enriched with deuterium. So this is the conclusion that made. This is the mechanism, not the earlier one. And that's it for today. And I'm not going to discuss this. And thanks to you. If you have any question, please let me know.
Sir, excuse me, sir.
Yes.
In the last mechanism,
Hmm.
deuterium is attached on the terminal carbon,
Yes.
not
Yes.
at the middle carbon, not at the middle inner alkene.
Hmm.
If it attacks inner alkene, what will be the case, sir?
Okay.
Inner alkene.
I will show you. So let me go to the first slide. So see if it is like this, it will attack D plus here. Okay, you got it.
Yes, sir.
Imagine in
Yes,
place
sir.
of H plus there is a D plus, deuterium plus.
Yes, sir.
So then this one second carbon will have deuterium, right? You got it.
Yes,
Okay.
sir. Yes, sir. Yes, sir.
So second, see this carbon is attacking this deuterium plus, and it will be this deuterium. It is not shown in the figure here actually. They have shown it CH2.
Okay.
So then there will be here in place of hydrogen there will be deuterium here. So if it is
In place of hydrogen, deuterium. Yes,
so
sir.
it can eliminate, and the deuterium should be present at the second carbon, number 2. Then there should be 2 deuterium should be here. But it is not what is observed. Actually what is observed is that this pi electron pushes here, and then the terminal carbon pi electron attacks the proton or deuterium plus, whatever. That's why they end up with more deuterium at the terminal center, which is the actual mechanism,
Sir,
that this is the mechanism.
which factor helps to push the electron, sir? Which factor helps to push the electron
Here
from
I would say that
a reset to?
mm, I would say that the stability of the carbocation may be the one factor. See, when you attack with the middle pi electron, so the carbocation which is formed benzylic,
Yes, sir.
meaning that only pH is stabilizing the plus charge here.
Yes, sir.
And if you show that the other way, that this pushing and then forming the carbocation, this carbocation relatively much stabler compared to the other one. See here, the pi bond is also conjugated and the benzene ring are also conjugated.
Yes, sir. Allylic and benzylic. Yes, sir.
Benzylic.
Yes.
So this is the favored way, I would say.
Yes. Thank you, sir. Thank you, sir. Very kind of you.
I hope it was good to all of you, Ankita and Paranatham. Sorry, I couldn't pronounce your name properly. Extremely sorry. And thank you for staying for a long time. Thank you so much.
Thank you, sir. Very kind of you, sir. Very kind of you.